In order to achieve the goal of increasing processing speed, further development is needed. Doing so requires us to break down the training pipeline and encoder integration into smaller tasks. Those tasks were extract data from existing encoding log files, design and train a neural network on prepared data, and integrate a neural network into pre-existing encoder solutions. The original design had us encoding a video and feeding the partition information into a learning algorithm to train a neural network. This required a log parser to be made to read the partition decisions of the VTM encoder and an AI platform such as TensorFlow to train a neural network. The hardware we need for this application is any Windows or Linux compatible computer. The project consists of various software subsystems mentioned in the project design. These subsystems were unable to be integrated with each other at this time. The subsystems would have worked together to make a functioning program that takes video data from the encoder, uses the Detectron-2 alongside a neural network to segment the video, run the segmented videos for a parser to find the types of splits used for each macro block, and then segments the videos in the VVC encoder using a binary output from the parser to decide which splits to be used. The required languages are Python and C++. It was decided mid-project that we would use the Detectron-2 platform to generate the segmentation information so the need to find a learning algorithm and train a neural network would be alleviated. As such, the log parser to retrieve the encoding information from a log was still developed in a Python script and output in text log to be used by the encoder. The log parser makes heavy use of regular expressions to retrieve attribute information about a block and nested dictionaries to index a block by frame and coordinates. Because of the inability to run the AI subsystem locally, all of the subsystems were tested independently of each other instead of as one large unit. This was not an issue, however, as each subsystem was tested based on the output of another subsystem. The AI subsystem had built-in error checks in the code, and the code was modified to pass these checks, giving the correct output. The data ingress subsystem had errors that were thrown if the parser achieved an undesired result, including the inability to match the text to an attribute or being unable to associate a block with a partition based on splitting logic. The code was modified as needed so the errors were not thrown in the process of parsing a log. The toggle subsystem ran the VVC encoder with the toggle variables both on and off. Encoding times and block sizes were compared to one another. When toggled off, the VVC encoder ran as normal. When toggled on, the VVC encoder ran using binary output of the parser to disable certain types of splits. The final plan ended up vastly different from the original plan. A majority of the tasks were divided into subsections over the course of a few weeks. The tasks reached towards a different end goal. Instead of creating an AI to make configuration file recommendations, the AI segmented the video in place of the VVC encoder. The goals that were completed was a toggle subsystem that was completed as far as possible as the current development state. It is able to hasten the segmenting process by disabling specific splits. The AI subsystem can completely segment a video much faster than the original VVC encoder. The data ingress subsystem is able to make segmentation data and turn it into binary information used in the toggle subsystem. The goals not completed was the subsystems were not integrated due to difficulties running the AI subsystem locally.
This is the AI subsystem for the deep video encoder, and I would run it for you, but that takes 13 minutes, so I'll just explain it. So these three functions are used to grab all the libraries necessary to run a segmenter, and the rest of it is a bunch of functions that actually segment the video. This is like the overview you put in the video, and it actually does all the segmenting. Uh, this function gets the frames from the video, as you can see here, and then each frame is done one by one. This function gets the mask of the current frame, and this function takes that mask and actually does the separation process. This is the first part of the separation process, which separates each frame into a basic 128 by 128 blocks, or smaller if is not divisible by 128 by 128. This function separates those 128 by 128 blocks into their actual block derivatives, and this function down here finds the upper left hand corner of those blocks. This function down here gets the version of the blocks in the regular frame, not the mass version. And this one put that information into the text file to recreate the segmented video. And these three things down here actually, allow you to run the video. This gets you through the video. This actually puts into the segmenter, and this allows you to get to the result. Anyways, so this was not able to be implemented with the other two parts because it's more accurate than the actual VVC in that it isn't limited to where it can place its blocks, although the block size is still limited. So it's not suitable to connect to the VVC encoder because its blocks might be in positions that the VVC encoder won't accept.
Okay, this is the script for getting the segmentation information from the pre-recorded log. So you would record a video in the VTM software unmodified, and it'll give you a log file of the encoding process. So you would, this is just command line thing so far. So you just do log parser.py and preface that with Python, which is in the file path. And you also, because it's not meant for the command line use, it is hard coded the file that's being rendered and hard coding the output file. But that could be easily modified. So right now I've removed all the print statements, so it's going to be very plain, the output on the command line. And the resulting log file is going to be something like this, where it's two-digit numbers in an array. There's 5 frames in the coded video that we did, so there's only 5 rows. And as you can see in the first row, every macro block in that frame uses both binary, which is the first digit, and ternary splits, which is the second digit. And you can see in the subsequent frames, there's a mix of not using any, using one, and using both.
Next up, we have the last unit in the fast versatile video coding project, the toggle unit. The toggle unit starts in the typedef.h file, in which the enable FVC variable is defined. This variable determines if the toggle unit is on or off, with a 1 being on and a 0 being off. This mainly affects the enc slice.cbp file, in which if the toggle unit's on, then it grabs a list of 2-digit binaries for each current frame. As you can see here, each frame is a different text file. Then, inside this loop, for every single macro block in the frame, it ends up using the enable FVC variable again, where if it's on, it says fast VVC encoder enabled, and then changes the maximum size for binary and ternary splits based on the current 2-digit binary. This either disables them or enables them. It grabs the current 2-digit binary for the macro block, and then if the binary is 00, then both of them are disabled and set to 0. If it's 01, then ternary is enabled and set to 32, but binary is set to 0 and it's disabled. If it's 10, then binary is enabled and set to 32, and ternary is 0 and disabled. And if the binary is 1, 1, then both of them have a maximum size of 32 and are both enabled. If any other value is entered that is not a binary value, then you get a valid entry. After that, compressed CTU is called, which basically divides the macro block into smaller blocks. As you can see here are the frame 0 and frame 1. Additionally, you can see the output blocks for both when the toggle unit is enabled and when it's disabled, which have the same output. Lastly, you can see the times right here. This is when the toggle unit is enabled, and as you can see, it's just under 30 minutes for 5 frames, and this is when the toggle unit is disabled, and as you can see, it's just under 50 minutes.